Imagine for a moment that reality itself might be nothing more than a shared agreement, that the solid ground beneath your feet, the screen you're watching, even the thoughts flowing through your mind right now, exist only because we've all collectively decided they should. What if I told you that some of the brightest minds in physics have discovered a paradox so profound, so unsettling, that it suggests there might be no such thing as objective truth at all? Welcome to a journey into the heart of quantum mechanics, where the very foundations of what we call real are quietly crumbling. I'm your guide through these mysterious waters, and tonight we're going to explore something that has been keeping physicists awake at night for decades. A paradox that doesn't just challenge our understanding of particles and waves, but threatens the entire concept of reality itself. So settle in somewhere comfortable, perhaps dim the lights, and prepare to question everything you thought you knew about the nature of existence. Before we dive into the depths of this mystery, I'd love to know where you're joining me from tonight. Are you listening from a quiet bedroom, perhaps with a cup of tea growing cold beside you? Or maybe you're taking a late-night walk, pondering the stars above? Wherever you are, take a moment to ground yourself in that space, because we're about to venture into territory where even the concept of where you becomes beautifully uncertain. For nearly a century, quantum mechanics has been the most successful scientific theory ever devised. It has given us lasers, computer chips, MRI machines, and countless other technologies that define our modern world. Every prediction it makes, every calculation it performs, works with stunning precision. And yet, beneath this remarkable success lies a troubling secret that physicists have been grappling with since the theory's earliest days. The secret is this: quantum mechanics works perfectly, but nobody can agree on what it actually means. It's as if we've built the most magnificent cathedral, with every stone placed with mathematical precision, but we can't decide whether we're looking at a place of worship, a fortress, or perhaps something else entirely. The mathematics is flawless, the predictions are accurate, but when we try to understand what the equations are telling us about the fundamental nature of reality, we encounter paradoxes that seem to defy logic itself. Think about this for a moment. We live in an age where we can measure the properties of particles smaller than atoms with incredible accuracy, where we can predict the behavior of quantum systems across vast distances, where we can even build quantum computers that harness these strange effects for practical purposes. And yet, after all these decades, after all these experiments, we still don't know what quantum mechanics is actually telling us about the world we inhabit. This isn't just an academic puzzle. This is a crisis at the very heart of our understanding of existence. Because if we can't agree on what quantum mechanics means, and if quantum mechanics describes the fundamental building blocks of everything that exists, then we're essentially admitting that we don't understand the basic nature of reality itself. Some interpretations suggest that particles don't have definite properties until they're measured. Others propose that every quantum event splits the universe into multiple parallel realities. Still others claim that consciousness itself plays a fundamental role in determining what becomes real. Each interpretation sounds more like science fiction than science, yet each has serious proponents among the world's leading physicists. But recently, a new paradox has emerged that makes all of these interpretations seem almost quaint by comparison. It's a thought experiment so elegant, so devastating in its implications, that it has forced physicists to confront a possibility that many had hoped to avoid, that there might be no such thing as objective reality at all. Let me paint you a picture that might seem absurdly simple at first, but contains within it the seeds of reality's potential undoing. Imagine two scientists, both highly trained, both using the exact same scientific methods, both examining the exact same physical system. Now imagine that these two scientists, through rigorous application of quantum mechanics, arrive at completely contradictory conclusions about something as basic as the outcome of a coin toss. This isn't a story about experimental error or faulty equipment. This isn't about one scientist making a mistake while the other gets it right. This is about quantum mechanics itself, predicting that two equally valid scientific observations can yield results that are mutually exclusive. One scientist can prove, using quantum mechanics, that the coin landed heads. The other can prove, using the exact same theory, that it landed tails. Both proofs are mathematically sound. Both follow the rules of quantum mechanics perfectly. As you sit there listening to this, take a moment to let that sink in. We're not talking about subjective interpretations or philosophical disagreements. We're talking about basic factual claims about physical reality that quantum mechanics suggests can be simultaneously true and false, depending on who's doing the observing. This scenario isn't just theoretical speculation. It's the heart of what's known as the Frauschiger-Renner paradox, named after the physicists Daniele Frauschiger and Renato Renner, who first formulated it in its current form. Their work represents an evolution of ideas that trace back to the 1960s, when the physicist Eugene Wigner first imagined scenarios where quantum mechanics might lead to such contradictory conclusions. The implications are staggering. If this paradox holds true, it means that science itself, which depends on the idea that different observers can agree on basic facts about the world, might be built on fundamentally shaky ground. It suggests that the very concept of objective truth, the idea that there are facts about the world that exist independently of who's observing them, might be nothing more than a comforting illusion. Picture this. You and a friend both witness the same event, perhaps a bird landing on a branch outside your window. In our everyday experience, you would both agree that the bird either landed or it didn't. Your agreement on this basic fact forms the foundation of shared reality. But according to some interpretations of the Frauschiger-Renner paradox, at the quantum level, there might be no such shared foundation. You might have valid reasons to conclude the bird landed, while your friend might have equally valid reasons to conclude it didn't. This isn't just a problem for physicists working with exotic quantum systems in laboratories. If quantum mechanics truly describes the fundamental level of reality, then these paradoxes apply to everything, including the neurons in your brain, the atoms in your body, the light entering your eyes as you process these very words. To understand how we arrived at this precipice, we need to step back and examine the strange architecture that quantum mechanics has built around us. For most of human history, we lived with a comforting assumption that the world exists in definite states whether we're looking at it or not. The moon is there in the sky, even when clouds obscure it. Your keys have a specific location even when you can't find them. Reality, we assumed, is objective and independent of observation. Quantum mechanics shattered this assumption with what might be the most counterintuitive concept in all of science: superposition. At the quantum level, particles don't just exist in definite states. They exist in combinations of all possible states simultaneously, until the moment they're observed or measured. It's as if reality itself is perpetually uncertain, wavering between possibilities like a coin spinning in the air, never quite landing until someone forces it to choose. But here's where things get truly strange. The act of measurement, of observation, doesn't just reveal which state the particle was in all along. According to quantum mechanics, the measurement actually forces the particle to choose a state. Before the measurement, it genuinely exists in all possible states at once. The observation literally creates the reality it observes. This idea troubled even the founders of quantum mechanics. Albert Einstein famously declared that he could not believe that God plays dice with the universe. He spent decades trying to find ways to restore objective reality to physics, to show that particles must have definite properties whether we observe them or not. But experiment after experiment confirmed the strange predictions of quantum mechanics, forcing scientists to accept that reality, at its most fundamental level, is far stranger than anyone had imagined. Now, pause for a moment and consider how this might apply to your own experience. As you listen to these words, photons are striking your retina, creating patterns of neural activity in your brain. According to quantum mechanics, each of these processes involves countless quantum measurements, each one potentially creating small fragments of reality in the very act of observation. In a sense, your consciousness might be continuously creating the reality you experience, moment by moment, through the quantum processes happening in your nervous system. This remains a speculative idea, not a proven scientific fact, but it hints at something profound about the relationship between consciousness and reality that we're only beginning to explore. The Frauchiger-Renner paradox takes these ideas to their logical extreme. It shows that if we take quantum mechanics seriously, if we apply it consistently to all physical systems, including the scientists doing the observing, we arrive at scenarios where reality itself becomes observer-dependent in ways that seem to violate basic logic. Let's walk through a simplified version of how this reality-breaking paradox actually works. Imagine a laboratory where quantum experiments are being performed by scientists who are themselves part of quantum systems. It sounds like science fiction, but it's actually a rigorous application of quantum mechanical principles to realistic scenarios. In this laboratory, we have what we might call nested observations. Scientist A performs a quantum measurement on a particle. From quantum mechanics, she can determine the her perspective using the rules outcome of her measurement. But Scientist B, observing the entire system, including Scientist A, applies quantum mechanics to a larger system that includes both the particle and Scientist A herself. Here's where the paradox emerges. Scientist B's analysis, following the exact same quantum mechanical rules that Scientist A used, can lead to conclusions that directly contradict what Scientist A observed. Both scientists are following the rules correctly. Both are using quantum mechanics as it's supposed to be used. Yet they arrive at mutually exclusive conclusions about the same physical event. It's as if two mathematicians, both using correct mathematical procedures, solved the same equation and arrived at different answers. But unlike a mathematical error, which can be corrected by finding the mistake, this contradiction seems to be built into the very structure of quantum mechanics itself. Take a breath here and let yourself sit with the magnitude of what this means. We're not just talking about a quirky feature of subatomic particles that doesn't affect our daily lives. We're talking about a fundamental breakdown in the logical consistency of our most successful scientific theory. If this paradox is real, it suggests that there might be no objective facts about the world that all observers can agree upon. Some physicists have responded to this paradox by suggesting that we need to abandon the idea of objective reality altogether. In this view, there are no facts about the world that exist independently of observation. Reality becomes fundamentally subjective, with each observer creating their own version of what's real through the act of measurement. Other physicists propose that we need to modify quantum mechanics itself, perhaps by introducing new mechanisms that prevent these paradoxical situations from arising. Still others suggest that consciousness plays a special role that breaks the chain of quantum observations before paradoxes can emerge. But perhaps the most unsettling possibility is that the paradox is real and that our entire notion of a single shared reality is simply wrong. Maybe there are as many realities as there are observers, each one equally valid, each one creating the act of observation, its own version of truth through. As we contemplate these possibilities, notice how they might resonate with your own experience of uncertainty and ambiguity in daily life. How often do you find yourself in situations where different people, all acting in good faith, arrive at completely different conclusions about the same events? Perhaps the Frauchiger-Renner paradox is showing us something that we've always known intuitively, that truth itself might be more fluid, more observer-dependent than we've ever been willing to admit. The journey we're taking together through these ideas is far from over. We've only begun to explore the depths of this reality-shattering paradox and its implications for everything we thought we knew about existence itself. In our next exploration, we'll dive deeper into the experimental evidence that supports these strange conclusions and examine what it might mean to live in a universe where objective truth is nothing more than a beautiful illusion. But for now, let yourself rest in the mystery. Let these ideas wash over you like waves on a distant shore, knowing that the deepest questions often don't have easy answers, and that sometimes the most profound insights come from learning to be comfortable with uncertainty itself. As we venture deeper into this quantum labyrinth, let me share with you one of the most unsettling experiments ever conceived by the human mind. It's called the extended Wigner's friend scenario, and it represents perhaps the clearest demonstration that our most fundamental assumptions about reality might be nothing more than comfortable illusions. Picture, if you will, a sealed laboratory. Inside this lab, a scientist, let's call her Alice, is conducting a quantum measurement on a single photon. From Alice's perspective, the measurement is straightforward. She observes the photon's polarization and records a definite result. Let's say she measures it as vertically polarized. For Alice, this is an objective fact about the world, as solid and undeniable as the weight of a stone in her hand. But now imagine that this entire laboratory, including Alice herself, is being observed by another scientist, Bob, who stands outside. From Bob's perspective, something extraordinary rules of quantum mechanics as happens. According to the long as Bob hasn't looked inside the laboratory, the entire system, including Alice and her measurement result, exists in a quantum superposition. Alice is simultaneously in a state of having measured vertical polarization and horizontal polarization until Bob decides to peek inside. Take a moment to absorb the strangeness of this scenario. We're not just saying that Bob doesn't know what Alice measured. We're saying that, according to quantum mechanics, Alice's measurement result doesn't have a definite value until Bob observes it. Alice's reality, her lived experience of having observed a specific outcome, is somehow suspended in quantum limbo from Bob's perspective. Recent experiments in Australia and Taiwan have transformed this thought experiment into mathematical proof, confirming what many physicists had feared, that this isn't just a philosophical puzzle, but a genuine feature of how quantum systems behave. The experiments use sophisticated setups with entangled photons serving as proxies for the human observers, but the logic remains the same. Two observers, both following the rules of quantum mechanics perfectly, can arrive at contradictory conclusions about the same physical event. What makes this even more disturbing is that both observers can be absolutely certain of their conclusions. Alice has directly witnessed the measurement result. Bob has applied quantum mechanics to the complete system and arrived at his own valid conclusion. Both are correct according to the theory, yet their conclusions are mutually exclusive. As you contemplate this paradox, notice how it might echo situations in your own life, where you found yourself in disagreement with someone else about events witnessed. Perhaps what you both seemed like simple miscommunication or different perspectives was actually a glimpse into something far more fundamental about the nature of reality itself. The mathematical formalism underlying these paradoxes is as elegant as it is disturbing. It's built on something called Bell's theorem, proven by physicist John Bell in the 1960s, which demonstrated that no theory of nature that respects both locality and realism can reproduce all the predictions of quantum mechanics. Locality means that objects are only directly influenced by their immediate surroundings. Realism means that objects have definite properties whether or not they're being observed. These seem like reasonable assumptions, almost too obvious to question. Yet Bell proved mathematically that if quantum mechanics is correct, at least one of these assumptions must be false. For decades, physicists hoped they could find loopholes in Bell's proof, ways to preserve our intuitive notions about reality while still accepting quantum mechanics. But experiment after experiment has confirmed Bell's predictions, culminating in work so definitive that it earned the 2022 Nobel Prize in Physics. The universe, it seems, really does violate our most basic assumptions about how reality should work. The implications ripple outward, like waves from a stone dropped in still water. If each other instantaneously, across vast distances, locality is false, then particles can influence, seemingly violating Einstein's relativity theory. If realism is false, then objects don't have definite properties until they're observed, meaning that the act of observation, literally, creates the reality being observed. Some physicists have tried to preserve both locality and realism by proposing hidden variable theories, suggesting that quantum randomness results from our ignorance of additional factors that completely determine system behavior. But these theories face their own challenges, requiring either faster-than-light communication or abandoning the idea that measurement outcomes are unique. Consider for a moment how this might apply to your own experience of making decisions. Traditional thinking suggests that your choices emerge from definite mental states, clear preferences, and logical reasoning processes that exist whether you examine them or not. But what if, at the quantum level that underlies all neural activity, your mental states exist in superposition until the moment you observe them through introspection? What if the very act of examining your own thoughts and feelings creates the mental reality you experience? This remains highly speculative, far beyond what current science can prove, but it hints at something profound about the relationship between consciousness and the quantum world that we're only beginning to explore. At the heart of all these paradoxes lies one of quantum mechanics' most mysterious features: wave function collapse. In the standard interpretation, quantum systems evolve smoothly and predictably according to Schrödinger's equation, existing in superpositions of all possible states. But the moment a measurement occurs, this smooth evolution suddenly gives way to abrupt, random change. The wave function collapses, and the system snaps into a single, definite state. This collapse is not gradual or partial. It's instantaneous and complete, as if reality makes a sudden decision about what should be real. But here's the troubling part. Nobody knows what causes collapse to occur, or even whether it's a real physical process or just a mathematical convenience. Some interpretations suggest that consciousness plays a special role in triggering collapse. The idea is that quantum systems remain in superposition until a conscious observer becomes aware of them. This view implies that consciousness is not just a byproduct of physical processes, but a fundamental feature of reality that helps determine what becomes real. Other interpretations propose that collapse occurs through interactions with the environment, a process called decoherence. Large quantum systems, like cats or human beings, interact with so many environmental factors that their quantum coherence is destroyed almost instantly, creating the appearance of definite classical states. Still, other interpretations, like the many worlds theory, suggest that collapse never actually occurs. Instead, every possible outcome of every quantum measurement happens in parallel branches of reality. From this perspective, there are countless versions of you experiencing different outcomes of quantum events, each believing that their particular branch is the only real one. As you listen to these ideas, pause for a moment and consider your own sense of continuity and identity. You experience yourself as a single, continuous consciousness, moving through time, making choices and experiencing their consequences. But if the many worlds interpretation is correct, there might be countless other versions of you, each with slightly different experiences, each equally convinced of their own reality. The measurement problem has haunted quantum mechanics for nearly a century, but recent developments have made it more pressing than ever. The problem can be stated simply: if quantum systems naturally exist in superpositions, and if measurements force them to collapse into definite states, then what exactly constitutes a measurement? This might seem like a technical question for physicists to sort out in their laboratories, but it touches on something much more fundamental. If we can't define what counts as a measurement, then we can't define when reality becomes real. The boundary between the quantum world of possibilities and the classical world of definite facts becomes impossibly blurred. Some proposed solutions are as strange as the problem itself. One suggestion is that measurements are triggered by the involvement of conscious observers, implying that consciousness plays a fundamental role in determining physical reality. Another proposal involves spontaneous collapse, where quantum systems randomly collapse on their own, with larger systems collapsing more quickly than smaller ones. Each solution brings its own philosophical baggage. Consciousness-based collapse suggests that mind and matter are more intimately connected than classical physics assumed. Spontaneous collapse implies that randomness is built into the fundamental structure of reality. Many worlds' interpretations suggest that everything that can happen does happen, somewhere in the infinite multiverse. Think about how these ideas might relate to moments of decision in your own life. When you're faced with a difficult choice, wavering between different options, what determines which path you ultimately take? Traditional psychology might point to rational deliberation or emotional impulses, but what if the process is more mysterious than that? What if your decision emerges from a kind of mental wave function, collapse, where multiple potential choices exist simultaneously until the moment you commit to one? This is speculative territory, far beyond what current neuroscience can confirm. But it illustrates how the measurement problem extends beyond physics into questions about consciousness, free will, and the nature of choice itself. Perhaps the most radical response to these quantum paradoxes is to abandon the idea of objective reality altogether. This isn't just philosophical speculation, it's a serious proposal by some of the world's leading quantum theorists, who suggest that reality might be fundamentally subjective, with each observer creating their own version of what's real through the act of observation. In this view, there are no facts about the world that exist independently of observers. When Alice measures her photon and records vertical polarization, she's not discovering a pre-existing fact about the photon. She's creating that fact through the act of measurement. When Bob analyzes the larger system and reaches a different conclusion, he's creating his own equally valid version of reality. This perspective, sometimes called cubism or quantum Bayesianism, treats quantum mechanics as a tool for making personal predictions about experience rather than as a description of objective reality. Wave functions don't represent the actual state of physical systems, but rather an observer's subjective degrees of belief about what they might experience. From this viewpoint, the Frauchiger-Renner paradox dissolves because there was never any objective fact for the observers to disagree about. Each observer creates their own reality through measurement, and these realities don't need to be consistent with each other. The implications are staggering. If this interpretation is correct, then science itself, which has traditionally sought to discover objective truths about the world, might need to be reconceptualized as a collective enterprise in reality creation. Different observers might literally inhabit different versions of reality, each one equally valid from that observer's perspective. As you procrastinate with your own experience of subject these ideas, notice how they might resective reality. Your consciousness gives you access to a rich inner world of thoughts, feelings, sensations, and experiences that no one else can directly access. In a very real sense, you already inhabit a subjective reality that's uniquely yours. Perhaps quantum mechanics is simply revealing that this subjectivity extends all the way down to the fundamental level of physical reality. While philosophers and physicists debate the meaning of these paradoxes, engineers and computer scientists are finding ways to harness quantum strangeness for practical purposes. Quantum computers, quantum cryptography, and quantum communication systems all rely on the same mysterious effects that create these reality-shattering paradoxes. Quantum computers work by maintaining quantum superpositions of information, allowing them to explore multiple computational paths simultaneously. The measurement problem that troubles theorists becomes a practical challenge for quantum engineers, who must carefully control when and how quantum systems collapse into definite states. Quantum cryptography uses the fundamental uncertainty of quantum measurements to create unbreakable codes. Any attempt to eavesdrop on a quantum communication channel necessarily disturbs the quantum states being transmitted, immediately alerting the legitimate users to the presence of an intruder. These technologies work despite our lack of consensus about what quantum mechanics means. It's as if we've learned to build cathedrals without understanding architecture, to compose symphonies without knowing music theory. The practical success of quantum technologies demonstrates that quantum mechanics captures something real about the world, even if we can't agree on what that something is. Take a moment to appreciate the remarkable strangeness of this situation. As you go about your daily life, using devices that rely on quantum effects, you're surrounded by technology that operates according to principles that seemingly defy logic and common sense. The smartphone in your pocket, the GPS system that guides you through unfamiliar streets, the medical imaging devices that peer inside your body, all depend on quantum mechanics in fundamental ways. In a sense, you're already living in a quantum reality, even if you don't usually think about it in those terms. The solid, predictable world of your everyday experience emerges from an underlying quantum foundation that is anything but solid or predictable. As we stand at this crossroads between classical certainty and quantum uncertainty, between objective truth and subjective reality, what does the future hold? Some physicists believe that new experiments will eventually resolve these paradoxes, perhaps by revealing new physical principles that restore objective reality to its throne. Others suggest that we're witnessing the birth of a new kind of science, one that embraces subjectivity and observer dependence as fundamental features of reality rather than inconvenient complications to be explained away. In this view, the quantum revolution is far from over. We're only beginning to explore what it means to live in a universe where reality itself might be observer-dependent. Recent advances in quantum technology are making it possible to test these ideas with unprecedented precision. Laboratory experiments can now create quantum systems large enough and stable enough to probe the boundary between the quantum and classical worlds. We may soon have experimental answers to questions that have been purely theoretical for decades. But perhaps the most intriguing possibility is that these quantum paradoxes are pointing towards something even more fundamental about the nature of existence. What if consciousness and reality are more intimately connected than we've ever imagined? What if the hard problem of consciousness, the mystery of how subjective experience arises from objective physical processes, is actually pointing toward the same deep truth that quantum mechanics has been trying to tell us all along? This is speculative territory, where science meets philosophy and both encounter mystery. But it's also where some of the most profound insights about existence might be waiting to be discovered. As you contemplate these possibilities, notice how they might change your relationship to uncertainty in your own life. Perhaps the anxiety we often feel when faced with ambiguous situations reflects a deeper truth about the nature of reality itself. Perhaps learning to be comfortable with quantum uncertainty might also help us navigate the inevitable uncertainties of human existence. The journey through these quantum mysteries continues to unfold, revealing new layers of strangeness with each passing year. What seemed like a minor technical problem in the interpretation of quantum mechanics has blossomed into a full-scale crisis in our understanding of reality itself. But perhaps that's exactly what we need. Perhaps our certainties about the nature of existence had grown too rigid, too comfortable. Perhaps these quantum paradoxes are inviting us to embrace a more fluid, more open relationship with reality itself. As we prepare to explore even deeper mysteries in our ongoing journey through the quantum landscape, remember that the questions we're asking together aren't just academic puzzles. They're invitations to wonder, to remain curious about the deepest nature of existence and to stay open to possibilities that might transform everything we think we know about what it means to be real. What happens when we take these paradoxes seriously and apply them to the most complex quantum system we know, the human brain? As you sit here, listening to these words, approximately 86 billion neurons are firing in intricate patterns, creating the rich tapestry of your conscious experience. Each neural firing involves quantum processes, ion channels opening and closing, electrons moving through molecular structures, all governed by the same mysterious rules we've been exploring. Some researchers have proposed, though this remains highly speculative and unproven, that consciousness itself might emerge from quantum processes in the brain. The idea is that the strange, non-local correlations we see in quantum systems might somehow give rise to the unified, coherent experience of being aware. Microtubules within neurons, some suggest, could maintain quantum coherence long enough to influence neural processing in meaningful ways. This is still very much in the realm of hypothesis rather than established science. The brain is warm, wet and noisy, conditions that typically destroy quantum coherence almost instantly. Most neuroscientists remain skeptical that quantum effects play any significant role in consciousness, but the possibility lingers like morning mist, tantalizing and elusive. Consider your own experience of making a decision right now. Perhaps you're wondering whether to continue listening or to pause and reflect on what you've already heard. In the traditional view, this decision emerges from classical neural processes, chemical signals cascading through well-defined pathways until they reach some threshold that tips you toward one choice or another. But what if there's something more mysterious happening? What if, at the quantum level underlying these neural processes, multiple potential decisions exist in superposition until the moment you become aware of your choice? This is purely speculative, not a proven scientific fact, but it hints at a deeper connection between the quantum mysteries we've been exploring and the everyday mystery of consciousness itself. The democracy of observations extends beyond individual minds to collective human experience. When multiple people witness the same event, we typically assume they're all observing the same objective reality. But if the quantum paradoxes we've discussed apply at larger scales, this assumption might be more fragile than we realize. Think about how often you found yourself in situations where different people, all intelligent and well-intentioned, walk away from the same experience with completely different understandings of what happened. Political debates, family discussions, even scientific conferences often feature exactly this kind of disagreement. Perhaps these aren't just failures of communication or differences in perspective. Perhaps they're glimpses into something more fundamental about the observer-dependent nature of reality itself. Recent experiments have pushed the boundaries of quantum strangeness to scales that begin to approach our everyday experience. Scientists have achieved quantum entanglement between objects visible to the naked eye, created superpositions that persist for measurable periods in relatively large systems, and demonstrated quantum effects in biological processes ranging from photosynthesis to possibly even bird navigation. These discoveries suggest that the quantum world isn't as separate from our classical experience as we might have assumed. The boundary between quantum strangeness and classical certainty appears to be more porous, more negotiable than early quantum theory suggested. In photosynthesis, for example, recent research indicates that plants might use quantum superposition to find the most efficient pathways for transferring energy from sunlight to chemical storage. The energy doesn't just follow one path through the molecular machinery of the leaf. It explores multiple paths simultaneously in quantum superposition before settling on the most efficient route. If this interpretation is correct, and it remains a topic of ongoing research and debate, then every tree in every forest is constantly performing quantum calculations, navigating superpositions of possibility to optimize its interaction with light. The natural world around us might be far more quantum than we ever imagined. Some researchers have even proposed that quantum effects might play a role in consciousness itself, though this remains highly controversial and unproven. The idea is that the brain's neural microtubules could maintain quantum coherence for brief periods, allowing quantum superpositions and entanglements to influence thought processes. As you contemplate these possibilities, notice how they might shift your relationship to the natural world around you. The next time you see sunlight filtering through leaves, you might wonder whether you're witnessing not just classical physics in action, but quantum computation on a massive scale. The boundary between the possible and the actual might be negotiated billions of times per second in the foliage above your head. Perhaps the most profound implication of these quantum paradoxes isn't scientific or technological, but artistic and spiritual. If reality truly is observer-dependent, if the act of observation literally creates aspects of what we observe, then we are all artists of existence, painters working on a canvas that doesn't exist until we begin to paint. This perspective, while speculative and not scientifically proven, offers a radically different way of understanding human experience. Instead of seeing ourselves as passive observers of an objective reality, we might be active participants in an ongoing act of cosmic creativity. Every moment of attention, every act of observation, every conscious choice might be a brushstroke in the masterpiece of existence. Traditional Eastern philosophies have long suggested something similar, though expressed in different language. The idea that consciousness and reality are intimately connected, that the observer and the observed are aspects of a deeper unity, appears in various forms across contemplative traditions. Perhaps these ancient insights and modern quantum paradoxes are pointing toward the same fundamental truth about the nature of existence. This doesn't mean that individual thoughts or emotions directly control quantum events or create physical reality through intention alone. That kind of magical thinking isn't supported by scientific evidence, but it does suggest that the relationship between consciousness and reality might be more intimate, more participatory than classical science assumed. Consider how this might apply to your own creative endeavors. Whether you write, paint, compose music, or simply navigate the artistry of daily living, you're already engaged in acts of reality creation. Your choices shape the world around you, influence the experiences of others, contribute to the collective human story. Perhaps the quantum perspective simply reveals that this creative participation extends deeper into the fabric of existence than we previously understood. As we near the end of our journey through these reality-shattering paradoxes, it's worth reflecting on what they might teach us about living with uncertainty. Classical physics promised a universe of definite facts, predictable outcomes, and objective truths. Quantum mechanics offers us something different, a universe of possibilities, probabilities, and observer-dependent realities. This shift from certainty to uncertainty might initially seem unsettling. We're creatures who crave predictability, who find comfort in knowing where we stand. But perhaps there's a different kind of comfort to be found in quantum uncertainty, a comfort that comes from embracing mystery rather than demanding resolution. The Buddhist concept of impermanence suggests that clinging to fixed ideas about reality causes suffering, while accepting the fluid, changing nature of existence brings peace. Perhaps quantum mechanics is teaching us something similar, that reality itself is more fluid, more open to possibility than our everyday experience suggests. This doesn't mean abandoning rational thought or scientific inquiry. It means holding our conclusions more lightly, remaining open to surprises, staying curious about the deeper mysteries that lie beneath the surface of our current understanding. It means cultivating what the Zen tradition calls beginner's mind, approaching each moment with fresh eyes, free from the assumption that we already know how reality works. As you listen to these words, take a moment to notice your own relationship to uncertainty. How do you feel when faced with questions that don't have clear answers? Can you find peace in not knowing, beauty in mystery, wonder in the face of the inexplicable? The quantum paradoxes we've explored together aren't just abstract problems for physicists to solve. They're invitations to a different way of being in the world, a way that embraces uncertainty as a fundamental feature of existence, rather than a problem to be overcome. If the many worlds interpretation of quantum mechanics is correct, though this remains unproven and highly speculative, then every quantum event creates new branches of reality. This means that, somewhere in the vast multiverse of possibility, every potential version of your life is being lived out by different versions of you. There's a version of you that made different choices at crucial moments, a version that pursued different dreams, a version that encountered different opportunities and challenges. Each of these versions is equally real from their own perspective, each convinced that their particular timeline is the only one that exists. This perspective can be either liberating or overwhelming, depending on how you hold it. On one hand, it suggests that you don't need to carry the weight of all the paths not taken. Somewhere, in some other branch of reality, you did take those paths. On the other hand, it raises profound questions about identity and meaning. If all possibilities are realized somewhere, what makes your particular experience special? Perhaps the answer lies not in the uniqueness of your particular branch of reality, but in the quality of attention you bring to it. Whether or not other versions of you exist in parallel worlds, this version, the one listening to these words right now, is the only one you have direct access to. This moment, this experience, this particular configuration of consciousness and reality is yours to inhabit fully. The many worlds interpretation remains highly controversial among physicists. Some embrace it as the most elegant solution to quantum paradoxes, while others reject it as untestable metaphysical speculation. But regardless of whether it's literally true, it offers a powerful metaphor for thinking about choice, possibility, and the paths we take through life. As our exploration of these reality-shattering paradoxes draws toward a close, let's take a moment to appreciate the gentle revolution that's taking place in our understanding of existence itself. These aren't dramatic discoveries announced with fanfare and headlines. They're quiet revelations emerging from laboratories and thought experiments, subtle shifts in perspective that ripple outward through our understanding of everything. The implications extend far beyond physics. If reality truly is observer-dependent, it changes how we think about truth, knowledge, and the nature of existence itself. If consciousness plays a fundamental role in determining what becomes real, it elevates the importance of awareness, attention, and mindful observation. This doesn't mean that science is becoming less rigorous or that objective truth is disappearing entirely. It means that we're discovering the limits of objectivity, the places where the observer and the observed become inseparably entangled. We're learning that the classical dream of perfect objectivity might have been just that, a dream. In its place, we're developing a more nuanced understanding of the relationship between consciousness and reality, one that acknowledges both the power of scientific method and the irreducible role of observation in shaping what we observe. This is a more humble kind of science, one that recognizes its own limitations while continuing to push the boundaries of human understanding. As you reflect on these ideas, consider how they might influence your own approach to knowledge and truth. Perhaps instead of seeking absolute certainty, we can learn to navigate uncertainty with greater skill and grace. Perhaps instead of demanding final answers, we can learn to ask better questions. The quantum paradoxes we've explored together represent just the beginning of a much larger mystery. Every answer we discover seems to reveal new questions, deeper layers of strangeness waiting to be explored. The more we understand about the quantum world, the more mysterious it becomes. This is as it should be. The deepest truths about existence aren't problems to be solved once and for all, but mysteries to be lived into more fully with each passing moment. The questions we've been asking together about the nature of reality, consciousness, and observation are questions that each generation must explore anew. Future experiments will undoubtedly reveal new aspects of these paradoxes, new layers of quantum strangeness that we can barely imagine today. Quantum computers will grow more powerful, quantum communication systems will span the globe, and our ability to manipulate and observe quantum systems will reach unprecedented levels of sophistication. But perhaps the most important discoveries won't be technological. Perhaps they'll be discoveries about consciousness itself, about the role of awareness in shaping reality, about the deep connections between mind and cosmos that these quantum paradoxes seem to be pointing toward. These are speculative possibilities, not established scientific facts, but they represent the kind of gentle frontiers that human curiosity naturally gravitates toward, the places where known and unknown meet in creative tension. Take a deep breath now, and let yourself rest in the vastness of what we don't yet understand. Let the mystery be comfortable rather than frustrating, inviting rather than threatening. In a universe where reality itself might be observer-dependent, your attention, your curiosity, your willingness to remain open to possibility becomes part of the creative force that shapes what through these quantum mysteries continues, not becomes real. The journey just in laboratories and academic papers, but in the quiet moments of wonder when you look up at the stars and remember that you're made of the same mysterious quantum stuff that fills the universe. In those moments, the boundary between observer and observed becomes beautifully blurred, and you become part of the ongoing mystery of existence itself. As we close this exploration together, remember that the deepest questions don't require final answers to be worthwhile. Sometimes the most profound insights come from learning to dance with uncertainty, to find beauty in mystery, and to remain open to possibilities that might transform everything we think we know about the nature of being real. If these quantum mysteries have intrigued you, you might find yourself drawn to explore how these same principles might apply to consciousness itself. In our previous journey together, we examined how meditation and contemplative practices might offer their own insights into the nature of reality, creating what some call the global consciousness experiment that's changing everything. These parallel explorations of inner and outer mystery continue to illuminate each other in surprising ways, suggesting connections between consciousness and cosmos that we're only beginning to understand. In the quiet spaces between thoughts, something extraordinary might be unfolding. As you sit here now, allowing these ideas to settle like morning dew on the landscape of your awareness, consider that every moment of attention you offer might be participating in something far more mysterious than we've yet imagined. The quantum paradoxes we've explored together don't exist in isolation. They're part of a larger tapestry of mystery that includes consciousness itself, that ineffable quality of inner experience that allows you to be aware of these very words as they arise in your mind. While science has made remarkable progress in understanding the neural correlates of consciousness, the hard problem remains. How does subjective experience arise from objective physical processes? Some researchers, though this remains highly speculative and unproven, have wondered whether the same quantum principles that create these reality-shattering paradoxes might also play a role in the emergence of consciousness. The idea isn't that your thoughts directly influence quantum events, but rather that consciousness itself might emerge from the same mysterious substrate that gives rise to quantum uncertainty and observer-dependent reality. Think about your own experience of being aware right now. There's something it's like to be you, listening to these words, feeling whatever sensations are present in your body, experiencing whatever emotions might be stirring. This subjective dimension of existence seems to stand apart from the objective world that physics describes, yet it's intimately connected to the physical processes happening in your brain. The measurement problem in quantum mechanics and the hard problem of consciousness share a curious parallel. Both involve the emergence of definite, concrete experience from a substrate that seems to resist such definiteness. Just as quantum systems exist in superposition until observed, perhaps consciousness emerges when the flow of information in complex systems reaches some threshold of integration and awareness. This is speculative territory, far beyond what current science can confirm, but it suggests that the mystery of consciousness and the mystery of quantum reality might be two faces of a deeper enigma about the nature of existence itself. If consciousness and quantum mechanics are indeed connected at some fundamental level, though this remains an open question in both physics and neuroscience, it might suggest something profound about the role of awareness in the unfolding of reality. Not that your individual thoughts control quantum events, but that consciousness itself might be woven into the fabric of existence in ways we're only beginning to glimpse. Consider how this might reframe your understanding of attention itself. In Buddhist meditation traditions, mindfulness is often described as a way of participating more fully in the present moment, of awakening to aspects of experience that usually remain unconscious. From a quantum perspective, though this is metaphorical rather than literal, we might think of attention as a form of observation that helps collapse the superposition of possibilities into the clarity of present moment awareness. When you notice your breath, for instance, you're not creating the sensation of breathing through observation. The physical processes of respiration continue whether you're aware of them or not. But your attention does seem to bring these processes into conscious awareness in a way that transforms your relationship to them. The simple act of observing your breath can shift it from an unconscious background process to a doorway into deeper presence and calm. This doesn't mean that consciousness violates the laws of physics or that meditation grants supernatural powers. It means that the relationship between awareness and reality might be more intimate, more participatory than classical science assumed. Your consciousness isn't separate from the physical world, observing it from some detached vantage point. It's part of the world, emerging from it, shaped by it, and perhaps in subtle ways, shaping it in return. As you explore these ideas, notice how they might influence your relationship to your own inner experience. Perhaps the thoughts and feelings that arise in consciousness aren't just private mental events, but aspects of the same mysterious process that gives rise to quantum uncertainty and observer-dependent reality. As we reach the end of our journey through these reality-shattering paradoxes, take a moment to feel the ground beneath you, the air around you, the simple fact of your existence in this moment. These quantum mysteries we've explored together aren't just abstract puzzles for physicists to contemplate in their laboratories. They're invitations to wonder, to remain curious about the deepest nature of what it means to be real, to be conscious, to be here at all. Whether reality is truly observer-dependent or whether consciousness plays a fundamental role in shaping what becomes actual, one thing remains beautifully certain. Your awareness, your attention, your willingness to question and explore makes you an active participant in the ongoing mystery of existence itself. The universe may be far stranger than we ever imagined, but that strangeness includes the remarkable fact that part of the cosmos has awakened to contemplate its own mystery. And that awakened part